Welcome back. We're now going to look at conditional statements. Why do we actually have to care about conditional statements? Let's get through here. So, control flow is about conditional execution. Now, this might sound like a whole bunch of mumbo jumbo words to you, given that I know most engineers aren't actual computer scientists. So, when we say control flow is conditional execution, what does it actually mean? I'm sure you're all very familiar from, say 1730, writing Python. Your basic if statements, for loops, while loops, etc. So when we say control flow is all about conditional execution, we're talking about statements like, if x equals 1, do this, else do this. So that's control flow and conditional execution, because we're conditionally doing something and changing the flow of our program. So here are some conditional expressions, and as the slide says, they all evaluate to true or false. So x can either be less than 13 or not less than 13. So this statement can be true or false, and the same goes for all the rest of them. Some of them get a little bit more complex. We can have multiple different things, and then we sort of just do some combinatorial logic to work out if the whole thing evaluates a true or false. And some of them might even be a function that returns true or false. So, in assembly, how might you do some of these? If you'd like to pause the video and have a quick think about it, I'll give you a hint. You'll want your status flags. Alright, we're back. Here's our status flag table. And we can see that we have the condition codes as you'd write in assembly, what these condition codes mean, and the flags they correspond to. So it might not seem intuitive, most of these, how they work. For example, why is the equal condition code mean that the 0 flag is set to 1, for example? Well, in a minute we'll get to some code examples and things will actually start to make sense. But we have a whole bunch of them. So equal and not equal are pretty simple. Negative or positive numbers, unsigned higher, unsigned lower or same, signed greater or equal, signed less than, signed greater, signed less or equal, etc. So we have our equal and not equal, and we have all kinds of greater, less, and greater, equal, less than, or equal for signed and unsigned numbers. We have some overflows, we have positives, negatives, carries. We have a whole bunch of different things we can use. So here's a very simple one. If x equals negative 24, we'll conditionally do something. Let's put this in VS Code. Okay. So let's see what happens here. So I'll put my then code label down here for a few knobs. So I'm adding these no-ops so we can see when we're stepping through whether or not we've actually done this branch here. Alright. So, what was our function? If x is equal to negative 24. Rightio. So, what I'll do here is we're assuming x is in R0. We'll put negative 24 in there and let's debug. Okay, so we have negative 24 in R0. If I put this in decimal, no, okay, so just remembering our 2's complement, negative numbers get represented like this. If you are confused about why negative 24 looks like that, I think we covered this in like week 2 or something. Anyway, it's the 2's complement representation of negative 24. And we'll do this add here. So we're adding negative 24 and 24. Okay. Where's our flags here? And we've set flags, and we've got a whole bunch of different flags here, including a 0 flag has been set. Now, I'm going to use set and clear here. Set means 1 and cleared means 0. So our 0 flag is set. And if we remember our BEQ, jump back to the slides very quickly, that's our equal, which means the zero flag is being set. We'll do whatever we have attached to this condition code. So our zero flag is being set in our program, and this is a branch equal. So we'll branch to then. So we skipped over here and we branched to then. So why are they equal? Well, that might not make sense really. We've added two different numbers and that says they're equal. But when we get a little bit further through this video, it'll start to actually click a little bit. For now, all we need to know is that branch equal or BEQ will happen when the zero flag is set, which it has in this instance. So let's say we've just put a different number in R0, like let's say we put 24 in here. So instead of negative 24, we've now got positive 24. And we'll run through our program. Step. We've got 24 now. 18 in hex is 24 in decimal. We'll add them together. And what flags did we set? We haven't got any flags set, so we're not going to branch. Okay, cool. So despite it's not making a lot of sense, we have actually implemented our function here. So if x is equal to negative 24, then we do whatever's at our then code label, otherwise we don't. There's a few other examples in here which you can do if you'd like. So this will do if x is greater than 10, using a sub instruction and the GT condition code, which is this one here, signed greater. And that wants the zero flag to be clear and the negative flag to be equal to the overflow flag. Some of these might start seeming a little bit weird, wacky, and esoteric, but you sort of just need to remember the meaning here. Okay. So using adds and subs, sometimes it doesn't make a lot of sense what's actually going on. So we do have some alternatives. There's always a couple different ways that we can use our flags and condition codes. And on this slide, I think it asks which is the best. So if I was a student who was, struggling to understand what all of these condition codes are and wondering why they all do different things and oftentimes don't make a lot of sense, I would say compare is a good one. Just let me check these slides very quickly. Okay. So why is compare good? Generally, compare will do what it says on the tin. In that, say I do compare R0, 10, and I have in R0 the number 10. So we'll run this. Now we've got our equals flag here. Now compare makes things all very simple in a kind of plain English way. So we can think of this as we're comparing R0 and 10, and then if they are EQ or equal, we'll branch to then. Okay, and we're there. So 10 and 10 obviously are equal numbers. So when we use a compare instruction, you can generally just read off the plain English meaning of the condition code. So compare will, tell you if the numbers are equal, if they're not equal. It'll tell you if they're greater or less than. So compare is the least confusing conditional checking instructions, shall we say. Now bear in mind, if we go to our cheat sheet here, so test instruction, there's a whole bunch of different tests and you can play with them in your own time to see what they do. Suffice to say, I would suggest that you just use compare. So compare doesn't actually change what's in the registers, it just compares them and updates the flags appropriately. Okay, so that's the conditional execution part of this video. If you're at all confused, please just open up VS Code, chuck in something very simple like this and just play with equals, play with, say, greater than, or I think less than, you know, there's all those different condition codes. Just put different numbers in and see what they do. Let's move on to doing some program flow. So there's a whole bunch of different ways that we can write, say, like an if statement. These are just a few different languages, but they all sort of boil down to the same kind of 4 major components. So we have expressions with a Boolean condition, so that means like, yes, like, these can be our 2 expressions, our 2 registers, and the Boolean condition is the equals in the middle, and then we have code for true and code for false. And how do these look in assembly? Well, what's wrong with this one? Hey, let's put this into VS Code and see what happens. So I'm just writing a very simple program here. I lost my main at some point. And okay, so we're going to put 10 in register 1 and 11 in register 2. Then our if statement here, I'll write this in sort of, you know, pseudocode. So what this is if R1 is equal to R2, then do R2 minus 1, else do R2 plus 1. So you can sort of see how this translates here. We've got if, we're checking if R1 is, we're comparing R1 and R2, and if they're equal, we're doing our then, otherwise we'll do our else. Now if you're looking carefully at what I'm doing here, oh excuse me, we got a bug, line 21. Solved. If you're carefully following along at home, you might have already realized that this isn't actually going to work very well. So we've got our 2 numbers in our registers. We'll compare them. Check our condition flags. So 10 is not equal to 11. So well, hang on a minute. If 10 isn't equal to 11, we should be going to our else then. So how does this work? It branches to then if they are equal, otherwise it does nothing and we just flow through here. So the way this if statement is written actually is never going to work. It's always just going to execute the then and the else statement. So let's go back to our slides here. And well, yeah, what are the problems with this? There are a few. It just doesn't work, does it? Just to save some time, I won't copy this one in because there's a better one on the next slide. Here's a better way to write an if statement. So if we do have our condition, we'll branch to then, but otherwise we'll branch to else. So that would be, you know, that'd be the same as doing be else here. So if we don't do our then we'll do our else, and we also need a be rest of program here. So this means it'll either branch to then and then jump over else, or it won't branch to then, it'll branch to else, and then we'll get to our rest of program. Well, we can do this with a few less branches. Here's how we do it. It's by rearranging the order of our code. So instead of having it arranged like this, what we'll do is, we'll put our else up here. Let me fix my indentation. Now, you shouldn't need to be a rocket scientist to work out that branch else, when else is the next thing, is completely redundant, so we can get rid of that. But we'll need to put our branch rest of program in here. Okay, wonderful. So what's this going to do? We'll compare our numbers. If they're equal, we'll branch over else to then. And after then, we'll go to rest of program. So we'll just keep executing along. If we don't go to then, we'll go to else. And we'll do this, and then branch to rest of program, jumping over then. So let's run this. Put our numbers in here. Bing, bong. Compare them. 10 and 11 aren't equal. 0 flag isn't set, so we won't take this branch. We'll do our else. And we'll skip over our then. Cool. So that works out as an if statement. Here's a fun example of a function that you could write. What does this do? Range less than. Oh yeah, calculates absolute values. Let's punch this in and see what it does. Excuse me, what did I put that there for? Okay. Now, you might have realized that this is referred to as a function here. And I guess the way we do functions in assembly, well, I don't think we actually cover functions until a later week, so let's just ignore that. But what we've got is some code that calculates the absolute value of a number. So what's absolute value? The absolute value of a negative number is the size of that number. So the absolute value of -5 is 5. Absolute value of -10 is 10, etc. So it's just the raw value of a number. You should know this from like high school math. Here's how the computer might do it. So if our number is equal to or greater than 0, it's already positive. We already have the absolute value. But if it's less than 0, so we've compared our number. Oh, rats. Okay, so R0 has -25. And we'll compare our -25 in R0 to 0. Now, obviously -25 is less than, or LT, so less than R0. We'll branch to then. And we'll put -1 in R1, and we'll multiply through. So a negative number times -1 is a positive number, results in a positive number. There we go. We have the absolute value of -25 in our register 0, which is 25. Cool. So that's just a nice little cute application of doing conditionals. Oh, sure. So label names must always be unique. Okay, so this video is already getting long enough. I'll cover loops in the next one.